In this video, we're going to continue the discussion about equinumerosity and establishing bijections between sets with the rational numbers. Now, we've been making implicit use of this concept already, but just to establish a definition, we're going to say that some infinite set is going to be countably infinite if and only if it is equinumerous to omega, which is a set of natural numbers. And just to remind you, we said that two sets, let's say A and B, are equinumerous if and only if there is some bijection f between A and B. So if it's possible to find some bijection between A and B, we say that they're equinumerous. And what we did last time is we found some explicit bijections for omega, omega times omega, and the set of integers z. That is to say, we found bijections between all three of these sets. First, we found a bijection between omega and omega times omega, and then we found a bijection between omega and z, and by extension, omega times omega and z. So we established that all three of these sets are equinumerous with respect to one another. And what we're going to do this time is investigate the set of rational numbers. In this video, I'm going to present two arguments for why the rationals should be countably infinite. And first, I'll present the standard argument that I believe Cantor used to argue for this fact. And it involves this table that we talked about last time, where you basically write out, or you establish the pattern for how you would write out any conceivable rational number on this table. So what you do is on the columns, you're going to write in the numerators 1, minus 1, 2, minus 2, and so on. And then the denominators, you just write out 1, 2, 3, 4, and so on. And then you take this snake-like path through the table. And what you're going to do is every time you cross a number, you just write it down. And then you're going to take care not to double count any numbers. For example, you wouldn't want to double count, let's say, 1/2 with 2/4, because we're going to say those are the same object. So when you do that, you're going to start at 0, then you make your way to 1, minus 1, 1/2, 1/3, minus 1/2, 2, minus 2, and so on. And you're going to write down that list like so. And the argument for writing down that list is that you can just associate any conceivable natural number, let's say 0, you can map that to 0, then you map 1 to 1, 2 to minus 1, 3 to 1/2, and so on. And by not double counting, you ensure that this map is injective. And by arguing that every single rational number that you can think of is going to be found somewhere on this table, this snake-like path will eventually make its way to it, and it will get mapped to by some natural number. And so the snake-like path is going to be a bijection if it has those two properties. And so you come to the conclusion that the rational numbers must be countably infinite. Now, I think this argument is perfectly valid. It does prove what it's intended to prove, that the rationals are countably infinite. It does suffer, however, from one weakness that we didn't observe in our previous bijections, in that in this description, I wasn't able to give you a formula which maps any natural number to its associated rational number. For example, when we mapped the naturals to the integers, I was able to give you a formula based upon evens and odds. In this sense, it might suffer from weakness if I asked you some questions like, which is the 10,567th rational number on this list? Now, the only way to answer that question in this method would be to actually, by brute force, write out all the numbers up to that point, being careful not to double count anything. Or if I ask you the reverse question, which natural number gets mapped to the rational number 97 over 146, you might have to do a similar sort of brute force computation. So in my second argument, I'd like to actually present a proof for the rationals being countably infinite, which actually gives you a formula to answer these two questions. Now, I claim this explicit bijection is going to involve two observations, really. The first is that every natural number, or every integer up to sign, has a unique prime factorization. That's the first fact. And the second fact is going to come from this bijection that we observed last time between the naturals and the integers, in that every even natural number can be mapped to 1/2 its value in the integers. That is to say, 0 is going to be mapped to 0, 2 is going to be mapped to 1/2 of 2, which is 1, 4 gets mapped to 2, 6 gets mapped to 3, and so on. And then the odds are going to take up the remaining positions. And the formula for that is going to be, you're going to add 1 to this value, and then you're going to divide by -2. So 1 is going to be mapped to -1, 5 would be mapped to -3, and as I said, the odds are going to take up the remaining positions. So what we're going to do is we're going to take any arbitrary rational number. Just to make it clear, I'm going to take an actual example first. Let's consider the rational number 2/9. Now the numerator is already in prime factorization form. 2 is a prime number. 9 can be written as 3 squared. So the prime factorization of 9 is going to be 3 squared. Now since it's in the denominator, I'm going to write 2/9 in the following way. 2 to the first times 3 to the -2. Now eventually I want to have this number, and I want to map it to some natural number. That is, some number without fractions in it. So what I'd have to do is I'd have to mess around with these exponents. And the way in which I'm going to mess around with the exponents is through this mapping here. It's actually going to be the reverse mapping, mapping the integers to the naturals. Now you can see that the integer 1 in this set gets mapped to the natural number 2. So that's what I'm going to do. I'm going to change the exponent 1 to a 2 there. And then I'm going to change this -2 here. If I look it up here, -2 in the integers gets mapped to 3 in the naturals. So that -2 exponent gets changed to a 3. So if I just multiply this stuff out, this is going to be 4 times 27. That gives me 108. Now I claim that what we've just done is we've mapped 2/9 to the integer 108. And let's say I wanted to map the negation of 2/9 or -2/9 to something. Then I claim I should just map 2/9 to -108. And if I wanted to go a little bit further, to map this rational number to an actual natural number, all I'd have to do is do this following procedure one more time. Just look up on this mapping between the naturals and integers what number 108 gets mapped to. Now 108, it's an even number, so I just multiply by 2 to get the natural number 216. Now in summary, what I've just done is I mapped 2/9 in the rationals to the natural number 216. And therefore I would map -2/9 to the number just before that, which is 215. Another strength of doing it in this way is that it's pretty clear, at least from a number theoretical point of view, that every rational number, let's say it's an a over b form, can be written in such a way where we have the prime numbers to a unique series of exponents. And it's also quite clear that if I go in the reverse procedure, any integer, again up to sign, can be decomposed in this way, where I have some product of prime numbers each raised to unique exponents. And I also know, just this mapping that I've given between the integers and the naturals, that that's also bijective. So there really isn't any place in this computation where I would lose the injective property. That's to say, there's no way that I'm going to have two different rational numbers which get mapped to the same integer or to the same natural number. And the reverse procedure, there's no way two integers or two natural numbers, because the prime factorization is unique, are going to get mapped to two separate rational numbers. So I claim this is, at least in this sense, just looking at this one computation, that this appears to be a bijection between the rationals and naturals, just by doing one computation. And next I'd like to show you how you can reverse this process. So in the first computation, we went from the rational numbers to an integer first, and then we converted the integer to the natural number. So let's try reversing this process. Let me give you the integer -2,148. And we're going to map that to some rational number. So I start out with that, and I just decompose that into its prime factorization. which is going to be 2 squared times 3 to the first times 179 to the first. Now here, 2, 1, and 1, these are going to be natural numbers. So to get things which are in ratio form, I'm going to map these natural numbers to the integers. So 2, if you look it up here, 2 gets mapped to 1, 1 gets mapped to -1, and again, 1 gets mapped to -1 here. So again, I've just messed around with those exponents a bit. Now I actually do this computation. So you can see in the new numerator, I'm going to have -2, and in the new denominator, I'm going to have 3 times 179, which is 537. So you can see here that the integer, negative 2,148, gets mapped to -2 over 537. And one additional thing to point out with this computation is that the thing you're getting out is guaranteed to be in reduced form. You're never going to get out of this computation something like 4 over 8, for the reason that you're sticking with the prime factorizations only. And one last note is that positive 2,148 would get mapped to 2 over 537. So the sign gets encoded very nicely. And one last example, let me consider the integer 73. Now 73 is a prime number, so its prime factorization is itself. So I can write 73 as just 73 to the first power. And again, I take the natural number 1, and it gets mapped to that integer, -1, and that gives me 1 over 73. So you see I start with the integer 73, and that gets mapped to 1 over 73. And actually that's going to hold true in all cases. If you have some integer which is prime, it gets mapped to 1 over that value, up to sign. So if you had negative 73, that would get mapped to negative 1 over 73. Or if you had, another example of prime would be 11. 11 gets mapped to, the integer 11 gets mapped to 1 over 11. Now that we've done a few computations, let's formalize what we're doing. Now here's this mapping from the naturals to the integers written out once again. To give it a name, let me call f. It's going to map the naturals to the integers. And again, if the natural number is even, I just divide it by 2. If it's odd, I add 1 and then divide by -2. And to put another name on it, I'm going to call the mapping that we've been doing from the integers to the rationals g. And thirdly, I'm going to write out the set of prime numbers. Well, you can actually write out the set of prime numbers, but I'm going to denote the set of prime numbers by capital P, the primes by P1, P2, P3, and so on. Now the argument is going to be as follows. For integers greater than 0, that is everything except 0 in the positive direction, let's call it x, it's possible to write out the prime factorization in the following form, where I have the infinite product through I, and it's going to be p to the I times some e to the I. That is to say, it's possible to multiply out all of the primes, and they're going to be raised to these unique exponents, the e sub i's. Now, what I'm going to do is I'm going to take that integer x, and I'm going to apply the function g to it, and the function g is going to be given by basically what we're doing before. We had those exponents, the e sub i's, and what I'm going to do is I'm going to apply that function f. Now, f was that function mapping the naturals to the integers to it. Now, that's just what we're doing before. For example, if we had the natural number 2, f would be taking 2 to 1. If I had 5, f would be taking 5 to -3. So that's just what we're doing before. And again, we're just dealing with the positives right now. Now, to complete out this function, this is what we're going to do for any positive integer, any integer greater than 0. I just apply this operation to it. If the integer is 0, I'm going to just map 0 to the rational number 0. And then if the integer is below 0, all I'm going to do is I'm going to apply the same procedure to the negative. That is, I'm going to just take out the sign. For example, if I had the integer -5, I'm going to apply g to 5 first, So I had that negative sign there, so it's going to introduce a double negative. I'm going to apply g to 5, see what I get out with that, and I'm just going to stick that negative out in front. So this is exactly what we're doing before. We just ignore the negative for now, and then we just add it out in front. So this function g, this definition of g, will take care of all integers. Now what remains is just to verify that g has the two properties that we want. For a bijection, it would have to be injective and surjective. Now to show that g is surjective, I could show that it has a right inverse, or I could more simply show that given any rational q, that is, if I start out with any rational q here, there's some x value, there's some integer, such that g of x equals q. And you can actually do that computation if you want. That's actually one of the exercises. Given any rational number in a over b form, write out its factorization and the primes, except these would be negative. These are allowed to be negative exponents now. And you can show me which integer x would have to be operated on by g to give you q. So that's basically how you show surjectivity. And I claim that g can be left inverted and is therefore injective. And just to remind you, left inverted means that given some integer, I can apply g first. I can take that integer to the rationals first, and then I can apply some other function, let's say g inverse, which takes that mapping in the rationals and it converts it right back to the thing I started with in the integers. And it's actually not difficult to write out what that left inverse is. And again, it's going to have to do with these exponents, because that's basically all we're doing in this computation is we're messing around with the exponents. And if you can find that left inverse, that would show that g is injective. And if you can show both of these, we can show that it's bijective. And therefore, we would have a one-to-one correspondence between the integers and the rational numbers, which is what we want. One last thing to point out here is that g, I claim, would give a bijection between the integers and the rationals. Now, if you wanted a bijection between, let's say, the naturals and the rationals, now that's very easy to show. And that bijection would be explicitly, it would be g of f. So f is going to first take that natural to some integer, and then g is going to take that integer to the rationals. So the composition g of f would be the bijection between the naturals and the rationals. So now that we've gone through the formal stuff, let's see some sample calculations for precisely that, g of f, which takes the naturals to the rationals. So in this first column here, I'm just listing out some of the natural numbers. In the second column, I apply f to the natural numbers to get their corresponding integer. And this is just what we're doing before with the evens and odds. And then g is going to take this stuff in the second column and it's going to map it to a rational number. So you can see here, if I start with 0, we said before that 0, really the integer 0 is going to map to 0. That's really the only exception case we have to worry about. And then you can see we're going to get the following stuff. Negative 1 is going to map to negative 1, 1 to 1, minus 2, remember 2 is prime, so it's going to map to negative 1 over 2. Same thing here. 3 is prime, so it's 1/3. And you can play around with some of these prime factorizations of the integers, and you can see that they're going to be mapped to pretty reasonable rational numbers. So that's one table there. As you get higher and higher, you get more interesting rational numbers. For example, when we get up to the natural number of 1,000, which would be associated with the integer 500, we would get 2 over 25. And then another interesting case, if you go a little bit further, well, actually not further, but before it, if you go to, let's say, 726, that's associated with 363, that gets mapped to 11 over 3, just another example. And so here are some other examples here. And I encourage you to play around with this. Pick your favorite rational number and see what integer gets mapped to it. So just to conclude this video, I've given two arguments for why the rationals should be countably infinite. That is to say that they're equinumerous to the natural numbers. We had that first argument, which is the standard argument often presented in math textbooks, which is given by Cantor. I think you might want to look that up. which was dealing with the snake-like pattern through the table. And then we just enumerate the rationals like we did before, just taking care not to double count any of those rational numbers. And then we had the second argument. I hesitate to call it a proof because I haven't seen it in too many places, so I just call it an argument for now. So if you're convinced by it, then wonderful, but it's just another way of looking at it. We had this number theoretic argument encoding the rational numbers based upon unique prime factorizations of the natural numbers, or of integers if you want to look at it that way. And of course there are strengths and weaknesses. The weakness to this one is that I haven't seen it around too much, so I'm not really sure that's a proof. I'm not sure that's completely flawless. However, this method does give you an actual procedure for converting one to the other, whereas this one does not. You would have to actually write out this list to answer the question, what's the 1/1,000,000th rational number in this list? But this first argument, this has been pretty well vetted in the math community, and this is pretty secure. And that's all I have for this video. Hopefully you've enjoyed this more computational approach for why the rational numbers should be countably infinite. And if you've enjoyed this video, feel free to subscribe and stay tuned for more videos. Thanks for watching.